All right, so what I'm going to do first is go over each of these problems and describe how you can code it. And then we'll go back and take your codes and go over them. All right. So first problem is taking an input S and returning the score and the identity. Okay. So this function needs to have a hard-coded target sequence. So what I mean by hard coding is you just need to write down a sequence. Let's say T equals AR and AR, TH, and so on. So you just have to write a random sequence like that. Okay. You can write your name if your name contains amino acid letters. So that'll be the target sequence. You need to return the global alignment score. So which function do I use for global alignment? NW, so the Needleman-Wunsch, NW align. So you need to get T with S, they'll give you the score. Okay. So that's all you need to return. Well, not all. You are also asked to return the identity. So what that means is you need to look at the alignment, the aligned positions, and see which ones are identical, and return the frequency of the identical positions. Okay. The NW align will give you multiple outputs. The second output is the alignment itself. So you need to capture both the score and the alignment from the NW align function. And the align variable here will contain the alignment itself, and it's a 3-row matrix. The first row contains the first protein or the first sequence. The third row contains the second sequence, and the part in between is just an annotation, a visual cue for showing you which amino acids are similar. Okay, so you only need the first and third rows out of the align matrix. You need to figure out how many times the first row is equal to the last row. So you need to find the positions that are identical between the first row and the third row. You don't have to worry about gaps because you will never, you are guaranteed not to have a gap aligning with a gap. So you need to just say align first row equal align third row. They'll give you a logical vector of zeros and ones, and you will have a 1 wherever the two residues from the first and third rows are identical. So they'll give you a logical vector. If you take the sum of that, they'll give you the positions that are identical, the sum of the number of positions that are identical. And you just divide that with the number of columns in a line. They'll give you the ratio of the aligned positions that are identical. All right. So they'll give you the identity value. The question is, the problem also asks you that if the two sequences are equal, then score should be infinite. Okay. The NW align will not return infinite when the two sequences are equal. It'll just be the alignment score. So you need to separately look to see if the two are equal, and that's just an str compare function. So at the top of your function, you should first say if str compare s and t. If they are equal, then you don't really need to do NW align. You can set score to be infinite and the identity to be 100%, and you don't have to look at the alignment itself. And you can either return from the function or wrap everything else with an else statement. Okay. Any questions about the fitness? Who's doing the fitness? Okay, good. Are you guys already done and it works? Okay. I did change things a bit from last week. I added this identity value. So last week you didn't have the identity. Okay. All right. You can sit closer if you'd like to solve it, or if you can communicate online. You don't have to do it separately. You can work on the same file. So you can upload a single file. All right, the second problem, who is working on it? Population init. Okay, so we have two groups. So this function creates an initial population as a cell array of size n. So we need n strings. We're going to have a cell array of strings. And each of these strings is going to be a random protein string whose length is randomly chosen between 1 all the way to max length. Okay. So first we need to randomly determine the length of the protein that we would like to generate. And then once we identify how long of a protein we are generating, each position is then going to be one of the 20 amino acids. So we again need to generate a random number between 1 and 20, and then convert that random number to an amino acid ladder using int to AA function. So you could do first, you will have a for loop, right? It's good practice to initialize your variable. Let's call it pop for population. You will have a cell array of 1 to n strings, so 1 row and columns. And then you will have a for loop that goes all from 1 to n, and you will then set the pop I. All right. So how do I set this? You could have another for loop here. First, let's identify the length of the sequence we are going to generate. So len is going to be a random number between 1 and max len. So you have to use the MATLAB's random function to generate a random integer between 1 and max len. There's a function called rand I that you can use to do that. Okay. And once you identify the len, let's initialize a character vector s equals, let's say character zeros 1 to len. I'm first creating a matrix, a numerical matrix of zeros, and its size is going to be len, and then I convert it to a character, so it becomes a string. And then you would have a for loop. Let's say j equals 1 to max len. Now I'm considering each position in the sequence, and sj is just going to be a random integer, rand I, one of the 20 amino acids, and you have to wrap that with into AA. Okay, so you generate a random integer, and then you convert it to a ladder. All right, so this will give you a random amino acid. S in its entirety is going to be the random string, the random protein that you generate, and the population is going to be the set of sequences that you generate. Okay, and you will return pop from your function. All right. So as a result, pop will contain a set of random sequences. Any questions? All right, good. Are you already done? Okay, good. Okay, thanks. The next problem, mutate, who's working on it? Okay, we have one mutate group. So the ones, if you are already done, you can start working on another function. Just so you have something when we start discussing, you can follow it easier. Okay, in the mutate function, we are asked to pick a random location and mutate it to something else. We can either substitute or delete or insert. So we take S. First, we need to pick the type of mutation that we want to do, and let's represent a substitution with 1, a deletion with 2, and an insertion with 3. So you will generate a random number between 1 and 3, and that will tell you which operation you need to perform. If that operation is substitution, then now you need to randomly pick a position. So again, it's a random number between 1 and the length of the sequence. Right? So pick a position, which is going to be a random number. and you take that amino acid, you convert it to a random new amino acid. A random new amino acid is just going to be int to AA rand I20. And it could happen that this new random amino acid would be the same one that was already there as one that was already there, but let's not worry about that. Okay. All right. So if it's a substitution, you do that. If it's an insertion, you will again take a look at this position and just split your sequence into before and after, and take this new random letter and put it in between. And you can just use vector indexing in MATLAB to do that. So you will go from S all the way to your location, okay, and then put your new random amino acid, and then append the location +1 all the way to the end. All right. Then your sequence will be one longer than it was. The last operation is a deletion. Again, you will use indexing. You can use indexing to create your new mutated sequence. You have your position. Your new sequence is just going to be S1 all the way to location, and then location +2 all the way to the end. So I'm skipping location +1. And it's up to you if you want to skip the location itself or location +1. All right. It would actually make sense to skip location, so let's do this log -1, and this one will start from log +1. All right. So it's just going to depend on how you represent log and index your sequence. Questions? Okay. All right. Who's doing the crossover? Okay. You can have one sequence to crossover. Okay. All right. So in this problem, we are given two sequences, S and T, and you are generating a new two new sequences which are crossover products of S and T, and we call them U and V. So this is very similar to the mutate in that you select a position, but now you select positions from both sequences. Okay, so this is a relatively easy problem. You have an S, you have a T, you pick a random position here, and you pick a random position in T, and you will just use indexing to combine the first portion of S with the last portion of T. That'll give you U, and the second portion of S with this first portion of T, and that'll give you V. Okay. All right. Population solve. Who's working on it? Okay. Did you already upload the crossover?
Yes.
Okay. You can work on the population solve. It's a more involved problem. Okay. So in population solve, we are putting everything together. Okay. First, we are normalizing these ratios so they add up to 1. So you would just take these numbers and divide them with their sum. So that's how you would normalize these numbers. You will call the pop init function. I provided the p files to you. You can use the p files. You don't need to wait for your friends to write the pop init function. Okay. You can use the p file that I provided. You will create an initial population. So there will just be a cell array of strings. And then you will have a for loop that goes all the way to max iterations. For each sequence in your cell array, we call the fitness function to find its score. So you'll create a vector of scores that contain the fitness values of each of the strings. And so if the best value did not improve since last 20 iterations, we stop the iteration. So to be able to do that, you need to keep track of the best values since last 20 iterations. So let's get back to this later. We are going to plot the best scores of each generation as the algorithm is running. Let's skip that again. We'll come back to it. And then we'll initialize next generation's populations to be empty. We are creating a new cell array that's initially empty. We'll pick the best ratio times n of the previous population from pop equals pop init. And we'll just move them to the pop next. So they go into the pop next as unchanged. All right. And since we say the fittest, these are the top, let's say 20% of them. We'll add an additional mutate ratio times n of them. But before we add them, we randomly chose them from the previous, from the fittest sequences, but we mutate them before we add them to the next population. All right. And for the last group, we randomly pick two sequences, and we cross over them and add them to the new population. All right. So we have three groups. The first group goes over unchanged. The second group gets mutated and added to the next population. The third group gets crossed over and added to the new population. Okay. And as an optional case, we are adding random sequences to pop init. And adding them to pop next, but also removing randomly from pop next. So the total number of sequences don't change. All right. And as we do this, we need to keep track of the best score, the best fittest value. Scores will be a vector, and you can just apply the max function to find the one that's scoring largest. And you will have another vector that keeps track of the highest value across different iterations. And if this number has not changed for the last 20 iterations, and to check if something has not changed in the last 20 iterations, imagine you have a vector of best values over all iterations. You would just look at the last 20, so 20 before the end, apply the unique function. The unique function will tell you how many different values you have. And if the number of such values is 1, that means the number has not changed. Okay. And at the end, we return the best sequence, which is described as the one having the best score. So this for loop is going to break in two different ways. One is if we've hit the maximum number of iterations, and the other one is if the score has not changed since the last 20 iterations. Okay. And the plotting will make use of the best scores across different generations. And you can see how the scores change. All right? Okay. So if you are working on the same problem, one of you can type and the other one can do backseat typing. It sometimes works better. And I'll give you about 5 minutes, and then we'll go over each of the solutions and discuss them. So in the first problem, we are going to calculate the fitness and as a global alignment score and the sequence identity. Let's look at the fitness function. All right. So these ASV files, you know what they stand for? Autosave. There's a MATLAB preference that allows you to change where these files are stored. I usually have them not saved in the current folder. Otherwise, it appears when you share them in your Dropbox folder and so on. Okay. You can find where it's located in your preferences and change it if you'd like. Okay. So the reason for this, one of the reasons for this exercise is to have you work with sequences and then show you how else you can do it. And one of the ways to show you the tricks is by modifying an existing code, which helps you learn. All right, so there's a short hard-coded target sequence. Because it's short, we are very likely to find it in our random population. The number of elements in T and S are given in X and Y. The question also asks you if S is a cell, then find the scores for each one. So if S is a cell array, then you would have to do the same operation more than once. So this particular solution checks if S is not a cell, all right, but it doesn't have, okay, if it is a cell, then we fall into this else part, and then they do something different, okay? But if you look at this code, you will see that this portion is identical to what's being done here, all right? So if the code is short, you can replicate it, but in general, when you program, try to avoid replication. Try to avoid copy and paste as much as possible. If you've already written something, it's better to try to make use of it. Okay, so what do I mean by that? If you call this function when S is not a cell, it'll go in here. But you can reduce the case where S is a cell by looking at individual entries in the cell array S and then applying the function to those entries. Okay? So if S is a cell, what I'm going to do is I'm going to delete these. And I will say for each element in S, for I equals 1 number of elements S. So S curly brackets I will be the individual sequence in S. So S is now a cell array of strings. And S sub I is one of these strings. And I can call the same function again, fitness map. So it's a recursive call. You are calling the fitness function on an individual entry of the cell array S. It'll go back into this function, but now it's no longer a cell array. Okay, so you unwrap a single entry and you call the same function again. It'll go in here next time. All right. So when S is a cell array like this, let's say this is the first one, A, C, A, H. This is the second one, A, T, W, and so on. S sub I is going to be an individual entry here. So it's just going to be a string. It's not going to be a cell array. A, C, A, H. Okay? And you take this, you pass it back to this function. And when you pass it, it will not be a cell array, so it will go in here. You are calculating the score and identity, and then it will return. When it comes back, you will have a score for this entry. And then you will do the same thing for the second one, third one, and so on. Okay? So I have a score vector and an identity vector. The ith score is going to be the is going to come from the ith sequence, and the ith identity is going to come from the ith sequence also. So I'll just do this: identity I equals fitness. Okay. All right. So if S is a cell, I do a for loop and calculate the score and identity for each entry. Let me pause my screen too. The projection device needs to rest a little bit. Now let's describe the case where S is a cell. If it's identical to T, score is infinite and identity is 100%. Otherwise, we do a global alignment, get the score, so that will be the score returned, and the alignment itself. The alignment is going to be used to calculate the sequence identity level. So identity equals number of elements where ALI is equal to this, divided by the maximum of length of X and the length of Y. So the second row in the alignment gives you the identical positions, but it's better to not rely on that and compare the first and third rows. So let's give an example. Score ALI equals NW align AC H A H. Okay. So ALI is a 3-row matrix. The first row is the first sequence, third row is the third sequence, and the second row contains these symbols. They are just visual cues that are not that I prefer not to rely on. A more robust way of finding the residues that are identical is to just check ALI third row. Okay, you'll get a logical vector. You can either take the sum of that will give you the number of identical positions. So you're just adding up the ones in there. There's another MATLAB function called NNZ, which runs faster. It counts the number of non-zero entries. So NNZ, number of non-zero entries. Okay. So let's take this. So there'll be the number of times we have one residue equals to the other one in the alignment. And so this particular solution uses the maximum length between X and Y. But for this problem, it probably makes more sense to use the alignment length. Okay. Yes, that's another option. So instead of finding the number of non-zero entries and dividing it by the number of columns, you can take the mean of that. Okay. So there are equivalent choices for the result that you get, but in terms of computational time, one may be faster than the other one. So counting is usually faster than summation. All right, just a small detail. And we don't need these X and Y variables anymore. And when you are organizing your code, I usually check whether something is a cell and then do the other one next. So if something's a cell, then we'll do this. Then we'll return from the function. And if something is not a cell, then we'll fall down here. All right. So this is how you would first solve the problem for a single string, and then to support S being a cell, you just add this code at the top, and then return from the function if it's a cell. So it's just a different way of organizing your code. Instead of if-else statements, you just check if S is a cell and then return. The main advantage from my point of view is that you don't have to indent these. Okay, so they just align to the left. It's easier to read your code if they are aligned to the left. If you don't have as many nested levels, it's easier to read the code. All right, any questions? All right. Okay. So let's go back. Let's go to the next problem, population unit, and examine the one that you submitted. Okay, so if n is not provided, meaning number of arguments is less than 1, we provide 0 arguments. It's initialized to 100, so that's the default value for n. The default value for max len is 100. We initialize a cell array of n entries, and for each entry, we create a random integer between 1 and max len, and then we create a random vector of numbers between 1 and 20, row and ps len of them. Okay. So when I described you the function, I told you that you can write a for loop where you would go over each position one by one. But this is more elegant way. You are making use of a vector of random numbers instead of a single random number. Okay. So rand I 20 gives you a single number. If you say 110, you'll get 10 random numbers between 1 and 20. Okay. And then if you wrap that with int to AA, int to AA function also supports vectors, so you don't have to give just a single number. You can give it a vector of numbers, and for each number it'll give you the corresponding amino acid letter. All right. So this is just MATLAB's encoding. It follows a conventional order that goes like A, R, N, D, and so on. So A is number 1, R is number 2, and 3, and so on. Okay. And to look up what MATLAB's conventions are, you can look at the documentation for int to AA. But in general, you don't really need to know which amino acid is which number. Okay. All right. So let's test this function. Pop init 3 sequences, each of them having at most 10 amino acids, and you get that. All right. Let's test the first function, fitness. Yes.
So when you say that Canadian is less than 1 and you say anything is 100, in that case, what will be maximum?
What will the maximum be?
I suppose I don't give any input, and it's
So
only for anything.
If you just do this, pop in it.
Yeah.
Okay, if you just call, there was a question, if I just say pop in it, what will the values for n and max len be? So when you say pop in it, let's go in here and debug it. The value for n argin is going to be 0. Okay, so this first expression is going to be true. We're going to go in there and n will be 100. And separately, this second expression is also going to be true. And then max len is 100. Okay. There is a way to organize these two if statements to avoid redundant checks. So if n argin is less than, the only way that n argin would be less than 2, the only way that n argin would be less than 1 is if it's also less than 2, right? So you can actually move this in here. Does that make sense? Okay. So if n argin is 1, that means n is provided. You'll go in here, set the max len to 100, but skip this one. All right. Okay. So the function will work the same, but you are avoiding this additional calculation if n argin is greater than 2, or if n argin is exactly 2. All right. Next function, mutate. Let's see your solution. And it's good practice to write your name in the functions that you wrote, so we can blame them for the errors. Okay. All right. So first we have a choice. Let's put semicolon so we don't print it in the command line. We have a rand I, and I don't really know how this works. Let me just check this. Rand I between, so I guess if I look at the documentation for rand I, instead of just saying 3, you can provide a range, and it'll give you numbers between that range. But since the first number is 1, you can skip 1 and just say 3. It'll be assumed that you are starting from 1. Okay. So let's just do that. We want to generate numbers between 1 and 3 that will represent the type of mutation we are performing. And then this particular solution converts the string S to a numerical vector by calling AA to N. And we don't really need to do this, but let's keep going, and then at the end we'll change it. Number of amino acids is N. If choice is 1, that means we need to substitute. We are finding a position that we will substitute. Okay, so the sub is represents the location. Okay, and then we just set a new random number there. If it's a deletion, we again get a random location represented by del and generate a new string, a new numerical vector in this case, that goes from the first position all the way to the del -1, and then we skip the del position and continue with del +1 all the way to the end. So effectively, by constructing this new vector, we are skipping the del position. So we are deleting that amino acid. Okay. In the last else if case, if the choice is 3, we are finding an insertion location and go all the way to ins. So we need to correct this one. So it should not be int -1 because we want to keep that location, right? We don't want to skip it like we did here. All right. We'll keep the insertion location, but we will add a new amino acid. In this case, the solution is adding the location itself as a number, which is incorrect. You need to add a new random amino acid. Okay? Make sense? All right. If you are generating only a single random number, you can skip the second argument and just say rand I20. So I'm picking the first ints positions from the original vector, adding a new random amino acid, and then continuing on with the last portion of the vector. And then finally, when all of these 3 cases are considered, I convert my numerical vector back to a character array. So numbers representing amino acids between 1 and 20 are converted back to letters of amino acids. All right, so I'm going to make some modifications in this function. The first one is that we don't really need to convert it to, so we can operate on S itself. So just bless you. I'm going to replace all of the num strings with S. Okay. But now, instead of adding a number here, you need to add a character. Okay. So in the first case where I'm doing a substitution, I'm generating a new amino acid, random amino acid, but I'm taking its character code and add it and insert it or substitute at that location. All right. There's another place that I am working with integers. I need to wrap that with int to AA also, so I would be adding a character to my string instead of a number to my string. Okay. All right. The other change I will do is change these else if statements to else if without space. Okay. So I have 3 different cases that are related. I don't really need a nested structure. And I'll just keep one of the ENDs. All right. So this will your code will look more organized. All right. So we have 3 different cases instead of creating nested else ifs. You can use this organization. The next change I will do is say switch choice, just to show you how you can do this with switch. If it's case 1, you do that. If it's case 2, you do that. Case 3, you do that. Okay, so your function will run the same way, but your code has a different organization. And let's change these. Rand I 1 ends with just rand IN. Like that. All right. So you are calculating a position in all 3 cases, right? So since we are guaranteed to find a random location for all 3 of them, we can move that out of the switch statement, so our code would be shorter. And I'll call this just a location and replace these with that. Look, and insertion location, let's call that lock also. All right. Okay. You can also move this random amino acid out of the way. It's not used in all 3 cases. It's only used in 2 of them. So it's up to you if you want to move it out or not. New amino acid equals that, and new amino acid. Okay. So let's run this function. Mutate FCC. You got question marks, 4 question marks, and so on. So there's an error here. Since it back to amino acids, we are already working in the amino acids with letters, so we didn't have to convert to numbers. That's why we had to delete the last portion where we are converting back to amino acids. Okay. Every time you perform a different mutation operation, and you work on a different location. Okay. All right. Any questions? Okay. Do I need the n, the length of s? Let's put semicolon there. All right. Next function, crossover. Okay, so if sometimes you may want to check the extreme cases if the rest of the code is not working for those extreme cases. If S is empty or T is empty, then you set U equals to be S and V equals to be T. Does that make more sense? You can still do crossover if one of them is empty, but that's okay. So one thing you could do is just ignore this part and see if the rest of the function works for these extreme cases, and they might. So in this example, in this function we identify 2 locations, 2 random locations, one from the first one from the second one. So the reason that they checked whether they were empty is because rand I 0 gives you an error. Okay, so you can't really check. You can't really have a random location out of 0 locations. That's why you have an error there. That's the reason they are checking this. Okay. So once you identify the 2 locations, U is going to be the first half of S all the way to that location that you picked, and the second part of T. And similarly, V is going to be the first part of T all the way to the location that you picked, followed by the second part of S. All right. So crossover ABC. I need to get two outputs, UB. So every time you call, you will get a different crossover event. To have it so that you don't have to you don't need these. I mean, to have it so that your code will generate a crossover even when one of the elements is empty. You could do, if S is empty, then location S. I'm just going to call this location S. S. And log T. So in this case, log S is going to be 0. Otherwise, log S is going to be rand I that. And if you are looking at the number of elements in S, length has a different, slightly different meaning. END. And we'll do the same thing for the string T. All right. And the rest of the function should work as it is. The reason we are safe now is that if S is a string, you can extract out S1 to 0 and it will work correctly. All right. So this will be an empty vector, meaning you are not indexing anything in S. You'll get an empty matrix. Similarly, 1 all the way to END, if S is an empty vector, will also work. It will give you an empty vector. So let's run the same examples again, cross over that. So it still works. If one of them is empty, it still works. Let's grab both outputs, UV. Okay. If they are both empty, then you will get two empty strings. Okay. All right. Since we are working with random strings, more or less anything is possible, so you do need to consider these extreme cases where one of the strings could be empty. The next problem is the population solve, where we will put these functions together to solve the problem. So if these parameters are not provided, you set the defaults. You need to do less bookkeeping if you use this other option where you check if the max iter variable does not exist. All right. So if you do it this way, then you don't have to remember. You don't have to go back and check the order of each argument. Okay. Cross ratio variable. So if that variable is not provided, then you set it to the default value. Well, I'll ignore the rest. We are normalizing three ratios. So dividing them by the sum will normalize it. We create an initial population. Pop next equals pop init. We are creating n. And we are not given the maximum length, so that's okay. And for each of the maximum iterations, we are collecting the best score, which is going to be a vector. And what does the plot score have? Nothing? Oh, I can delete it. Okay. And we are creating the figure, initializing the figure. X is going to be the number of iterations, and Y label is the score during that iteration, the maximum score of the individual. For each iteration, we set pop to be the population from the previous iteration. Okay. So this is after we are done with this iteration, pop next is going to be the new pop generation, and then we just set pop equals pop next to move over to the next generation. Okay. We calculate the fitness of each member. So that's the scores. Score is now going to be a vector. And so that the highest score comes first. All right. And the reason we need this IDX score is so that we can sort the population in the same order. And I would, do you do sorting of the population somewhere here or no? No, okay. So you need to sort the population in the same way so that the population strings in the population correspond to the scores that you have sorted. So the highest score, which is the first score in the score vector, is going to correspond to the first string in the pop cell array. Okay. All right. So now I have this population and a score vector. You have it down there somewhere? Okay, I'll delete it or I'll move it up. So you have a string here and its score. You have another string here and its score. So that's how we got this, and then we sorted the scores so that the first one is the highest, and we sorted the population in the same order so that the score matched up with the individual string. We are keeping track of the best scores in the population, so that's going to be the first one in the score vector because we sorted them. And then at this point, you can plot it. Where's the plots? At the end? Oh, here you go. Okay. So let's just plot it, get the plot out of the way. And if the fitness did not improve since the last 20 iterations, that means you need to check. You need to check that you've actually run this for loop at least 20 times, and that the last 20 are all the same. Here in the solution, they are using a separate variable flag, but you can actually use the best score itself to do that. So let me do it that way. If iteration is more than 20 and number of elements of taking a unique of the last 20 scores, END minus 19 all the way to END is 1. So what I'm doing is I'm looking at the best scores that I have accumulated over different generations, over different iterations. I'm looking at the last 20 of them, and then I'm applying the unique function, which will give me the unique numbers out in that vector. If they're all the same, then the unique set will contain only a single element. So I'm checking whether the number of elements of the unique values is 1. And if so, I break. That means things have not changed over the last 20 iterations. That means the population is probably stuck somewhere and they cannot really improve over their best individual, the best sequence that is in the current population. All right, so now we are going to generate a new population from the current one. Pop next is initialized to be empty, and best ratio times n of them are copied from the previous population. And we look at, since they are sorted, they are using the IDX score here, so let me pick the top, let's say 5 or whatever this number is. All right. And then we are adding an additional portion by mutating them. Pop next, seal. So let me look at this. We look at the best ratio of this, and so let me introduce a new variable here, top k equals this one. So that's going to be the top k entries in the fittest set. Okay, so that top k gets copied as they are, and then I'll copy this many over by mutating them, and I will pick them from rand I top k. So the top k sequences from the pop contains the top k most high scoring individuals, and I'm randomly picking one of them. All right, and I'm mutating it, copying it over to the next population, to the next generation. In the last group, now I need to pick two, just like this one. When I pick one, now I need to pick two out of the current population and cross them over, move them to the new one. So let's use this code to pick an individual from the current population. And do it twice. We may pick the same individual, but let's ignore that. All right. Add additional random sequences. So what this will do is rand 1 to 5. Okay. So you delete 5 of them and you add 5 new sequences to your new population. All right. So since you are doing floor and ceilings here, it may be the case that you are reducing the population size by 1 or increasing it by 1 if n is not an even number. So to keep the population size the same, you could do if pop next, well, pop next is greater than n, then just pick the first n of them. Else, if it's smaller than that, then generate new ones. Pop next, end plus 1 all the way to n equals pop init n minus. Okay. So if there are more than n, you get rid of the extras. It just generate new random sequences. And the best score and the index of the best one is done this way. We don't really need the index. Since the scores are ordered, the best score is just going to be best score. Actually, we do. Okay. So it could be the case where the population finds a good individual, but because you randomly change things, in next iteration, you may have a less score. Do we ever get that in this implementation? Yes, because of this part where you randomly remove individuals and randomly add new ones, you may remove the top highest scoring individual. So in the new generation, you may have lost the best scoring individual from the previous population. Okay. So when you look at the best scores over time, things can go down also. So they do not necessarily go all the way up. So you need to look at all the previous iterations, find the one that performed the best, and pick out the individual from that. Okay. And to be able to do that, pop no longer keeps track of the individuals in the iteration that gave the highest result, right? Pop is the latest population. You actually lost the population that gave the highest result. So to solve that problem, whenever you find the best score, you also need to keep track of the best sequences. Okay, so best score is going to be the one that is the largest value, and best sequence is going to be the individual with the highest score. And in this case, best sequence, best IDX. Okay. All right, let's run this. Hopefully it'll run without errors. Pop solve. Let's remove this one. F5. We got an error. When you run your MATLAB, if you get an error and your execution exits, you can type db stop error so that it will stop where an error happened so you can examine your variables. Let's go to editor and change the stack to where we actually call the NW line. We called it here. Let's look at S is an empty vector, T is the target. So there's a special case where S is an empty vector, and NW line doesn't support that. So if one of the strings is empty, NW line gives you an error. So what we could do is handle that special case ourselves. If S is empty, then what would the score be? Score is going to be putting gaps everywhere, right? Score equals, let's check the default gap penalty. I think it's 10. Gap. -8, okay. So the default gap is -8. Score is just going to be -8 times number of elements in T. And identity is going to be 0%. Else, we use NW align to solve the global alignment for us. Let's run pop solve again. And you see the population changing, and you get the result infinite, which means you actually solved the problem and you found the sequence. The plot stopped right here. I don't know why. Let me double check the pop solve to see where we did the plotting. So we are iterating but not finding the best score. Oh, okay. So if the best score is infinite, the plot function doesn't show it. Okay, so it ignores the values that are infinite. You will not see it on the plot. Let's get the score and the sequence that we find. And we should find the sequence that's hidden in the fitness function, so FFC. Let's have another one. So it took it about 12 iterations to find the sequence. So as you can see, we already know that we should also stop if the value is infinite. If the score is infinite, we've already found the answer, and we cannot really improve beyond that. So in addition to breaking, if the fitness does not improve in the last 20 iterations, we can also say if the best score is infinite. Now it'll stop as soon as it finds an infinite score. Okay, 20 iterations. All right. So why do we have to do this? We are doing things randomly anyways. Why not just generate random sequences and evaluate whether they evaluate their score and just pick the highest one? So why not generate? Let me give you an example. Why not generate 10,000 sequences? And then apply the fitness function. Find the maximum score. Find the location of the maximum score and pick that sequence. So finding the fitness value takes a long time. Index equals maximum scores, and then this is the that performs the best. Why did I get this? Oh, all right. Now I should work. So this is the best scoring one from my randomly generated set. So why is the genetic algorithm performing much better than just simply generating enough random sequences to find the correct answer? Any ideas? You have some comments? It's what? Um, I can hear the first part. If there's logical rules? Biological rules. Yes and no. So the reason that this genetic algorithm works is not because we are emulating the biological rules underlying sequences. Genetic algorithm is just it's a greedy optimization algorithm, meaning you have a set of solutions, you know how good they are, and you just try to make them better. All right. Instead of doing it flat, generating 1 million random sequences and picking the best one, we are generating, let's say, 100 sequences, but making them better and better over time. And that has a better chance of finding the optimal solution. Okay. And the operation mutation brings us closer because every time we mutate, we again reevaluate its fitness. If it improves, we keep it in the population in the solution set. If it doesn't, we get rid of it. But each iteration, we only keep the most promising ones. The crossover makes it so that if two individuals are good, so let's say they are solving different parts of the problem, so they are good at different aspects. All right. When you cross over, you are likely to take the portions from each that are good and combining their best parts to generate a better individual. Okay. So you are more likely to generate a better solution to a problem than just generating things randomly. And this genetic algorithm, you don't have to apply it just to problems of sequence alignment or sequences. You can apply it to any optimization problem where you can represent your entities, your solutions in the form of a vector, and that you can define operations on these solutions to change them. Okay. Sometimes for some problems, crossover may not make sense, so you can only mutate them. Okay. All right. Any questions, comments? All right. In that case, it's 1 p.m. It's the end of the class, right? Okay. So we'll see you next week. and I'll post it online. Yes, the one that we were supposed to today, so that I didn't cover.
So we don't have a midterm.
We'll have a